Hi class, this is section 3.3 and we're going to be talking a little bit more about probability, the multiplication rule, the addition rule, and you're probably going to find this is a lot of review from the previous section. As I'm getting used to this book, I'm noticing some of what I was teaching you in 3.2 they continue into 3.3. So what's going to be really good about that is it's going to give you a chance to practice some more. So the first thing, we did talk about the multiplication rule before, and we said the multiplication rule, we're going to use it when there's two or more trials, and it's that idea that you take the probability that A occurs and then the probability that B occurs. And the way that we're going to find that is we're going to multiply. And that, you could think of the asterisk as a multiplication, or you can put a dot in there. The way you find the probability of A and B is you take the probability of A multiplied by the probability of B, hence the multiplication rule. The thing that can make it tricky is that you have to when you're figuring out the probability of the second event, you have to consider that the first event already happened. So sometimes that probability changes. And that would be if you have dependent events, events when there's no replacement. And I believe what this book did is in 3.2, most of the events were independent, and in 3.3, most of the events will be dependent. So the next thing that we'll look at is the addition rule. And the addition rule, we will get more into this when we start working with tables. But the addition rule, if you have the word or, you want to add the two probabilities together. And this part here, right now in this section, it's not going to make a lot of sense. You're not going to need it in this section. But what that means is if there's any overlap between the two events, you don't want to double count them. And like I said, we will look at that in the next section when we'll be looking at tables and organizing our probabilities using a table. Okay. I want to look at a bunch of examples just to give us more practice. And again, probability does tend to be one of the more challenging topics for students. So I feel like the more opportunities to practice, the better. So this first one says we have a box and it's filled with party favors. It has 12 hats, 15 noisemakers, 10 finger traps, and 5 bags of confetti. So we can see here what's in that box of party favors. I think it would also be helpful to get the total. So that's what, 27, 37, 42. So now, first thing we're going to look at, if we can choose one item from the box. So you're at this party and they say, okay, go pick something out of the box, and you can't see what's in there. So you reach in there and we want to know what's the chance that you get a hat. So a hat, there are 12 hats out of 42, and then we would simplify this if we wanted it as a fraction. I'm okay with you just getting it as a decimal. So we have 12 out of 42, which is 0.286. This is your work, so you want to make sure to show the fraction. This is your rounded result. We wanted to find probability. If it asks for a percentage, you would move the decimal 2 places. It did not ask for a percentage. And watch for that on my open math. It will have the little percent sign if they want the answer expressed as a percentage. Typically in statistics, we will use the decimal for probability more so than percent. Okay, let's look at the next one. So this one has the word or in there, and we're choosing one item. So again, my little trick is I think of that one blank that I'm filling in. We want a hat or a finger trap. And when we were up here, we said for or we want to add. So there are 12 hats, there are 10 finger traps, so this would be 22 over 42, and 22 out of 42 is 0.524. Okay. So that really isn't much different than what we were working on before, just a little more practice. So now the next one we're going to look at, it says if you choose two items from the box. So this time we're going to go in the box, we're going to grab one item and another item. So because it's an and, we're going to multiply. So I'm going to have two different blanks to fill in. First, we want to get a hat. So what's the probability we get a hat? 12 out of 42. And means multiply. What's the probability that we get a noisemaker? And this is where we need to be careful because we already grabbed that hat out of there. So now there are only 11 hats. And there's only 41 total items. So when we go to get the noisemaker, it would be 15 out of 41. And that's what in the multiplication rule it means given the previous occurrence of A. So you've got to think about what happened in your first trial and how that's going to impact the results of the probability in your second trial. Sometimes what will bother students is they'll say, well, I don't know whether they replaced it or not. They didn't say. The assumption is no replacement. If it's being replaced, they'll tell you. The assumption is no replacement. Let me put here, assume no replacement. Okay, and so now if we're finding this probability, you can enter this in your calculator just like this, 12 divided by 42, and if you look at your graphing calculator, there's your fraction, times 15 divided by 41, and we'll get 0.105, and I did round that. Oops, there we go. Okay. So the next one, we're still choosing two items. 1, 2. We want two finger traps. So we want in the first pull, in the first trial, there's an I squeezed in there. You want a finger trap. And in the second one, you want a finger trap. I'm used to those. Those are the little, like, I think they're called a puzzle, or you put your finger on either side and you pull it and you try to see if you can get your finger out. So in the first pull, we're trying to get a finger trap. And I'm going to go back to where we were with our total of 42. The finger traps, there are 10 of them. 10 out of 42. We take one out, and now there are 9 out of 41. So 10 out of 42, excuse me, times 9 out of 41, 0.052. All right, we're still choosing two. This first one here says you want a hat or a noisemaker and a finger trap. So this one has an or. So this is the hats plus the noisemakers and the finger traps. First pull and second pull, or first trial, second trial. So we reach into that box with all the goodies and we want a hat or a noisemaker. We're going back to the beginning again. We want a hat. There's 12 hats. Or a noisemaker. There's 15 noisemakers. So 27 out of 42. We have a pretty high chance of getting a hat or a noisemaker. So as far as looking at this, we pulled one thing out. We don't know if it was a hat or a noisemaker, but we know that our total changed to 41. There would be 10 finger traps left out of those 41. So 27 out of 42 times 10 out of 41. 0.157. And you'll notice I am not getting this value as a decimal and this value as a decimal and then multiplying it. You want to save your rounding until the very last step. So putting this fraction in here and putting this fraction in your calculator and keeping all the decimals, this is the only time you round. Because if you round here and you round here, it's changing your results more so. Okay, last one. It says now we get to choose 3 items from the box. So first, second, third trial. So whatever we get here and whatever we get here and whatever we get here. So a hat and a noisemaker and a finger tap. So first we reach in there. What's the chance we get a hat? 12 out of 42. And after we take out that hat, what's the chance that we get a noisemaker? 15 out of 41. And what's the chance we get a finger trap? 10 out of 40. Excuse me. So 12 out of 42 times 15 out of 41 times 10 out of 40. And I'm just checking my work. That's one nice feature of your graphing calculator. You can see the display. 0.026. Okay. So a suggestion, when you're doing things like this, having this organized and easy to look at helps. Also, my little filling in the blanks helps. Considering the word and means multiply, that helps as well. And then again, like I said when we talked about the names in the hat in the previous section, you're reaching in, you're grabbing something out. Think about how that affects the total and how that affects the other items. Okay, so again, this probably feels very similar to what we did in section 3.2. You're getting a little more practice. I think you'll find there are more where the total is going to change in this section. Okay, this next thing is not in the book, at least at this point in time, and I want to make sure you learn this. So this is something that we would typically discuss, and it's finding the probability of at least one. And maybe I should say something like finding the probability of at least one A on your report card, or finding the probability of at least one job offer, or finding the probability of at least one head when you flip a coin. So this word, at least one something, there's going to be a formula that we can use to find this. And you can see the formula is right here. And actually, I'm going to put it in red because it's almost that I want you to have like a red flag go off or red flag that you think about when you see the probability of at least one? So the first thing I want to do is build the concept. I want to show you where that formula comes from and why it is what it is and why it helps us, why we even care. So what I want to look at first is we talked about the rule of complementary events. So this is building the why of the formula. And we have the event A, and we have the event A with the bar. You could also do A prime. Your book does A prime because it's easier to type. And the rule of complementary events said the probability of an event plus the probability of its complement equals 1. So we said, like the probability of winning plus the probability of losing, one or the other is going to happen. So that gives you all the possibilities. So that's why it's guaranteed you're going to get one or the other. The probability is 1. All right. So here's what I want you to think about. If A is at least 1, what would not A be? Because that's the complement. So at least 1 head when you flip a coin. Well, if it's not at least 1, what would it be? I want you to think about it. If I said you had at least 1 A on your report card, if you did not have at least 1 A on your report card, the complement of at least 1 is none. If you have at least 1 car, if you don't, then you have no cars. I say none. You could also say no. So this is the event. This is the complement. So the probability of at least 1 plus the probability of none equals 1. It's just an extension of that rule of complementary events. And then we can solve for the probability of at least 1 using algebra. I'm going to subtract the probability of none from each side. And we're going to have 1 minus the probability of none, which is what I have boxed there. As we do the examples, I'm going to hopefully help you see why this helps us, why this is so important. Again, if what I just did, you're going, I don't completely get it. The important thing is that you remember the formula. And it's probably on your stats formula packet. I'll have to check. If not, you can write it in. And you want to remember, in a problem, in a, if you have an exercise you're trying to figure out, if you see the probability of at least 1 whatever, then you're automatically going to say, ooh, I need to use that formula. Okay, let's look at the first example. And the first example says, find the probability of having at least 1 girl if a family plans to have 3 children. And I intentionally am giving you the words because I want to make sure you can get to the symbols. So it says find the probability. So we're finding the probability that this family has at least 1 girl And it's out of 3 children. So we could say out of 3 kids, or you could just remember here we're talking about 3 kids. So we can do this using the formula, and I'm going to in a minute, but I want to reason it through. If we didn't have the formula, having at least 1 girl out of 3 kids. So you have your 3 kids. The first one could be a girl. The middle one could be a girl. The last one, the youngest, could be a girl. All of those situations have exactly 1 girl. You could have 2 girls. They could be the first 2. They could be the second and the third. They can be the first and the third. You could also have 3 girls. So you could have this or this or this or this or this or this or this. And you'd have to add all of those up, all of those probabilities. What's easier, because we have at least 1 here, we say, oh, we have this formula. 1 minus the probability of none girls. I know that sounds funny. In some ways, it might help you remember it more. No girls. Okay. How many kids is this family having? 3 kids. None of them are girls. Well, if none of them are girls, they're all boys. How many kids are we having? 1, we. How many kids is this family having? 3. What's the chance that the first one's a boy? 0.5. What's the chance that the second one's a boy? 0.5. What's the chance that the third one's a boy? 0.5. 1 minus 0.5 to the third. This is first one's a boy and second one's a boy and third one's a boy. 1 minus 0.5 to the third. Whoops. 0.875. Okay. We took that one situation where there are no girls, and we know these all have to add up to 1. So instead of adding this plus this plus this plus this plus this plus this plus this, we just took away the one situation we didn't want. It's pretty smart. Also, we're only talking about 3. What if we had 10? Or what if we had, what does that show? 22, or, you'd have to go through all those possibilities. You would get the same answer, but it would not be as efficient. So if I had done this, it would be 0.5 times 0.5 times 0.5. 1, 2, 3, 4, 5, 6, 7. 0.5 times 0.5 times 0.5. And then we'd have to add them. So times 7. If you multiply by that by 7, you get 0.875. So you can either find all those and add them all, or do this. So this is the preferred, more efficient method. Okay. So this part over here, I'm just kind of going through to give you a little more of the why, so you understand why we're doing it. Okay, that way it won't be so cluttered up. Next one we're going to look at, I'm going to leave that formula up there. This one says 24.9% of robberies cleared with arrests. A new detective is assigned to 10 different robberies. Find the probability that at least 1 robbery cleared. So I'm going to write that down. Probability that at least 1 robbery cleared with an arrest. So out of the 10, at least one cleared. So they arrested somebody, and at least one. So it could be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. So you don't want to have to go through all those possibilities. When you see at least one, your brain, I hope, will start to say, oh, at least one is 1 minus the probability that none, and then don't just put none, put none cleared. None of those 10 cases had an arrest. Okay. The other thing that I like to do is I write down what I know. In the beginning, it said 24.9% of the robberies cleared with arrests. So the probability that it cleared with an arrest is 24.9%. Now, typically, if they give you the percentage, you're going to want to write the decimal. So the probability that a robbery cleared was 0.249. Let's get this. Probability that it didn't clear. Well, those are complements. It either cleared or it didn't. Those are your only two options. So we would go 1 minus 0.249, 0.751. So this is what we have to work with. Over here now, we're going back to this side. 1 minus the probability that none of them cleared. None cleared out of 10. It's a lot. So the first one did not clear, and the second one did not clear, and the third one, and the fourth one, and the fifth one. So this will be 0.751 to the 10th power. Don't forget to subtract it from 1. It's really common for students to forget that. So writing all of this down is showing your work, and it's also helping you get the correct answer. So it's 1 minus 0.751 to the 10th. 0.943. If you were going to try to go through all the combinations, here's what I want you to think about. You have 10. If it's at least one, it could be the first one, or the second, or the third, or the fourth, or the fifth, or the sixth, or the seventh, or the eighth, or the ninth, or the 10th. It could be the first two. Or it could be, the first and the third, or the first and the fourth, and the first and the second. Think about how many different combinations, because it's at least one or two or three or four. To go through all of those possibilities would take forever. This is a lot more efficient. Okay. Erase. Last example. Find the probability that Bruno gets at least one date if he asks 5 different women. Assume that the probability that someone says yes is 0.4. So the probability that he gets a yes is 0.4. And you'll notice it says 0.4. When numbers are typed, if they just typed a 0.4, it might be easy to not see the decimal. So that's why we use the 0 as a placeholder. In math, it's not necessary. If you're going into the medical field, though, they are going to want that 0 in there, because if you're prescribing medication, and let's say you did 0.4 milligrams of something, and somebody didn't notice your decimal, it was too light, then they might give the patient 4 milligrams, which would be 10 times the amount they should get. So if you're going into the medical field, and there are quite a few people in our class that are going into nursing, make sure you include that 0. For me, it doesn't matter. And again, it's not 0.04, it's 0.4. So the probability that one of these women says yes is 0.4. What's the probability that she says no? We're not talking about maybes. She either says yes or she says no. Those are complements. So the probability that she says no would be 0.6. So I got this from the problem, and I'm going to use that now. It says find the probability that he gets at least one date. And he's asking 5 people. There's that at least one. 1 minus the probability of none dates. I know that sounds weird, but that's okay. No dates. Well, he's asking 5 people. 1, 2, 3, 4, 5. The first one says if he gets no dates, the first one says no, and the second one says no, and the third one says no, and the fourth one, and the fifth one, and. They're independent events because the person that he asked, I don't think they're going to know that the other person said no. So this is 1 minus 0.6 times 0.6 times 0.6. So that's going to be 0.6 to the 5th. All 5 people said no. And we get 0.922. And now let's think about this from the standpoint of this guy. 0.922. That's a pretty high probability. If we think about probability again, going from 0 to 1, that 0.922 is pretty close to 1. So I would think he'd be in pretty good shape as far as having at least one date. Okay? So there are a few of the at least ones in there. If you look for support in the book, it's not in this section, but there are some on My Open Math. And I felt like it was important for you to see that. The other thing, you're going to get more practice with these as far as the no replacement. And then remember, addition rule or means add. And the multiplication rule and means multiply. So moving forward, the next section we're going to look at tables. And the multiplication rule and the addition rule will apply for the tables as well. Okay, you can go ahead and work forward. Have a good rest of your night.